All right, today we're diving into something pretty wild, the connection between quantum physics and high finance. We're going to see how a totally new kind of algorithm can tackle one of the oldest problems in the book, how to build that perfect investment portfolio.
So here's the fundamental problem, right? Whether you're trying to find the fastest delivery route or, in our case, picking the best mix of stocks and bonds, you're facing an optimization challenge. And when the number of choices gets massive, millions or billions of possibilities, finding that one single best answer is, well, it's next to impossible for a regular computer.
And this is where things get weird and really powerful. A classical computer is like someone trying to solve a maze by running down one path, hitting a wall, backing up, and trying another, one by one. It's methodical, but it's slow. A quantum computer, because of this mind-bending idea called superposition, it can basically explore every single path in the maze at the exact same time. It's a completely different way of thinking about problem solving. So here's our game plan. First, we'll really dig into what this optimization puzzle is. Then we'll meet our quantum tool, something called QAOA. We'll use it to build a portfolio, and then we'll pit classical versus quantum in a head-to-head race. Finally, we'll get real about what this all means for the future.
Okay, let's dive right in. To solve a problem, you first have to understand its shape, and the underlying structure of our financial puzzle might not be what you expect.
At its heart, our big fancy finance problem is actually a bit like a classic puzzle called the max cut problem. Imagine you have a bunch of dots connected by lines, and your job is to draw a circle that splits them into two groups, maximizing the number of lines that cross from one group to the other. Now, what does that have to do with finance? Well, you want a portfolio of assets that don't all move together. The math for separating those dots is actually incredibly similar to the math for finding that perfectly diversified portfolio. Okay, so now we get the shape of the problem. Let's talk about the specific quantum tool we're going to use to solve it. It's called the Quantum Approximate Optimization Algorithm, or for short, QAOA. QAOA is a really clever mix of old and new. It's a hybrid algorithm. That means it uses a quantum chip to do the heavy lifting of exploring all those possibilities. But it uses a regular classical computer to be its guide, to steer it in the right direction. It's designed to find good enough answers, which is absolutely perfect for the kind of noisy, imperfect quantum computers that we have today. So how does this thing actually work? Well, it's kind of like a loop. First, the quantum computer puts itself into a superposition of all possible portfolios at once. Then it does two things, over and over. A cost step gently nudges the system towards the better answers, the portfolios with higher returns and lower risk. Then a mixer step lets the system kind of jump around and explore other, different combinations. And that classical computer is in the background, tweaking the settings for that nudge and that jump, until a quantum system naturally settles on the best possible answer. Okay, enough theory. Let's make this real. Let's see this algorithm actually do its thing on a small, but totally realistic financial problem. Here's our mission, plain and simple. We've got 4 different assets to choose from. We have to pick exactly 2 of them. The goal? Find the one pair that gives us the absolute best bang for our buck, the highest return for the lowest risk. So let's meet the contenders and our miniature market. We have equity. Think of it as high-growth stocks. It's got a great potential return, but it's also pretty volatile. Then we have bonds, still a solid return, but with about half the risk. Then there's gold, the classic safe haven. And finally, good old cash, which is super stable but doesn't offer much growth. Each one has a very different personality. And I just love how the source material describes these. It gives them real character. Equity is at the edge of exuberance. Bonds are sympathetic to equities, which is a fancy way of saying they tend to move together. Gold is walking its own quiet path. It does its own thing. And cash is just sleeping lightly beneath them all. Understanding these relationships is everything. All right, the stage is set. Our players are ready. It's time for a showdown. First, we'll find the best portfolio the normal way. Then, we'll see if our quantum contender can match it. First up, the old school approach. We just tell a regular computer, check everything. There are only 6 possible pairs here, so it just calculates the risk-return score for each one and finds the best. And the highest possible score it can get is 0.071. That's our benchmark. That's the number to beat. And the winning combination is equity and gold, which, when you think about it, makes a ton of sense, right? You're taking the high-octane growth potential of stocks, and you're balancing it out with gold, which kind of zigs when everything else zags. It's classic portfolio theory in action. So this is the moment of truth. Can our quantum algorithm,
which isn't checking things one by one, but is exploring this whole landscape of possibilities at once, can it land on that same single best answer? And the answer is a huge yes. I mean, look at this. It's not even close. After we run the QAOA algorithm and measure the result, over 99% of the time, the answer it spits out is the correct one: equity and gold. The quantum approach worked. It navigated that whole complex space and absolutely nailed the landing. Okay, so it worked. The quantum algorithm found the right answer. That's awesome. But what does that really mean for us right now? And what does it promise for the future? Let's be super clear about something. For this tiny little problem with only 6 options, the classical brute force method is way, way faster. But that's completely missing the point. This experiment was never about speed. It was a proof of concept. You can think of it as a rehearsal for scale. It proves that this new approach works so that one day we can unleash it on problems with billions of combinations, problems that classical computers could never brute force their way through. Now, we're not living in a quantum future just yet. We have to be realistic. There are some serious hurdles to overcome. Quantum bits, or qubits, are incredibly fragile and get thrown off by the tiniest bit of noise. And the bigger the problem, the more steps you need in your algorithm, which just gives noise more chances to creep in and cause errors. Not to mention, just getting all the financial data into the quantum computer in the first place is a huge challenge. And this is really the journey we're on. Right now, we're in what people call the NISQ era. That stands for Noisy Intermediate Scale Quantum. These machines are amazing for research like this, for proving concepts. But the real revolution comes with the next generation, the FTQ, or fault-tolerant quantum computing era. Those are the machines that will be stable enough and powerful enough to actually deliver a true quantum advantage. You know, what's so cool about this whole experiment is how it shows these two different worlds, finance and physics, are speaking the same language. Things like risk and correlation can be translated directly into quantum mechanics. It really suggests that, at the end of the day, a Wall Street trader and a quantum physicist are both on the same hunt. They're searching for the ideal pattern hidden inside a whole world of probabilities. The question isn't if this will change things, but just how big that change is going to be.